The next factor that's very important we do talk about is the effect of adding a catalyst. So a catalyst, this time for a catalyst, it doesn't affect the curve itself. Okay, the curve remains unchanged. The distribution of particles remains the same, but activation energy shifts. Okay, so the presence of a catalyst provides an alternative reaction pathway which lowers the activation energy. So this alternative pathway has a lower activation energy. How it comes about, you don't need to know. Okay, later on, when you progress further in chemistry, you realize how certain things can be used to lower the activation energy. Right, and because the activation energy is lowered, you realize again, more particles have energy greater than the new activation energy. So you have more effective collisions, the frequency of effective collisions increases, and hence the rate increases. Again, for this, please memorize this. Okay, so with that, you are now ready to do self-check question 9. Here is a summary table of the various tricks that we can do to try to increase the rate of a reaction. But note that although we increases the rate of the reaction, how they affect the rate constant, how they affect the activation energy is all a bit different. Okay, please take a look at the summary. So realize that for the rate constant, the only things that can change the rate constant is the increase in temperature and the catalyst. As for activation energy, only a catalyst can lower the activation energy. Note that temperature does not affect activation energy. Right, now let's move on to catalysis. Since we are on the issue of catalysts, it's only natural to move on. So, what is a catalyst? So it's a substance that increases the rate of a chemical reaction with itself being regenerated or chemically unchanged at the end of a reaction. Just now we already gone through some mechanisms. You've seen how the catalyst is regenerated at the end. Right? So that is a catalyst. But it does, again, just because it's regenerated doesn't mean it can't appear in the rate equation. It can appear in the rate equation. Okay? So please be very careful about this. Let me write it down. Okay, so the rate equation is not always just reactants. It can involve catalysts as well. Now, what are some characteristics of catalysts? They do not change the enthalpy change. Enthalpy change reaction is not affected by catalysts. They do not increase the yield of products. They only increase the rate at which products are formed. And they are usually chemical involved in the reaction. Okay? Consumed in one step, regenerated in a subsequent step, used repeatedly without undergoing any permanent change. So that's why, right, very often catalysts, you'll see catalysts appearing in rate equations because they are lowering the activation energy of the slow step. So the slow step is no longer so slow, right? So for it to be no longer so slow, that's because its activation energy has been lowered. And why its activation energy has been lowered? Because the catalyst was involved. Now, very interestingly, there's a negative catalyst, or what we call an inhibitor. Right, so these are the opposite of catalysts. They will decrease the rate of reaction. You may think, why we want something that can decrease the rate of reaction? Yeah, sometimes we need it. And biology, in biology, this is a very important point. Okay, so students who study H2 biology, you'll know more about this. So those of you who don't know, you may want to find out more. You can go and ask your friends. Now, energy profile diagrams, we talked about it before in energetics. So we'll talk about it again here. So energy profile diagrams, you'll note the delta H, no change. The only thing that changes was the activation energy. Uncatalyzed was E1, much higher. But catalyzed, it lowers it by use of an alternative pathway. So it becomes lower, becomes E2. So because it's lower activation energy, the reaction becomes faster. Now let's talk about the different types of catalysis. Essentially, there are two main categories. We'll break them up into homogeneous and heterogeneous catalysis. Then, in addition to homogeneous and heterogeneous, there are two more specific types. What we call autocatalysis, which is a subset of homogeneous generally, and biological catalysis, that's again a subset of homogeneous catalysis. Okay, so let's take a look at the first category, heterogeneous catalysis. So heterogeneous refers to the state. Hetero means different. Okay, you say heterosexuals. Okay, it wasn't homosexuals. That's just one example. Okay, yeah, off the top of my head. So hetero just means different. So in this case, heterogeneous means different physical states or phases. Usually, a heterogeneous catalyst is a solid that catalyzes a reaction between gases or reactants in solution. So it works by providing a surface onto which reactants are adsorbed and from which products are desorbed. Please note the spelling is a bit unusual. This one is not a B, it's a D. Okay, adsorbed. Will Cambridge penalize you on this? I'm not sure. But as much as possible, try and use the correct terminology. Now, generally, heterogeneous catalysts are metals, or at least they possess D subshells. Okay. Okay, not just D lah. F block also. Okay. So they allow the ready exchange of electrons between transition metals. Okay, because D and F block metals, these are what we call as transition metals. You'll learn this in J2. Near the end of the syllabus. So, because of this ready exchange of electrons, they will form weak bonds. So, the adsorption of the reactants onto the catalyst surface will also cause the bonds within the reactant molecules to be weakened. Right? So, there's less activation energy. And because they are on the surface, okay, on the surface, instead of a 3D space to move around, they are now all stuck in the 2D space. The concentration naturally, the surface concentration of the reactants naturally increase. Okay, so once the reaction happens, the products are formed, they are then dissolved from the surface of the catalyst. So this is a very simplified example. Okay, so it shows the hydrogenation, the reaction of between and what we call an alkene and hydrogen. Okay, so just to say again, the H2 is adsorbed on the surface, the alkene is adsorbed on the surface, they are all adsorbed. Okay, then the bonds are weakened. So because the bonds are weakened, it's easier for the H2 to react with the alkene. After reaction, then the whole thing can be dissolved. And this is the product. So this is your heterogeneous catalysis. Another example, these are the few that you need to know because it's in the syllabus. How do you know it's in the syllabus? Well, they stated it. Okay? So examples 1, 2, and 3 are all to do with heterogeneous catalysis. So first one, Haber process. We'll use iron powder to optimize, to speed up the reaction between nitrogen and hydrogen to form ammonia. You may say, where are all the details? The details will be in chemical equilibria, which is actually the next chapter, in fact. Okay, and why I don't want to talk this one, why we don't talk about the catalysis here is because you'll notice, hey, this is a reversible arrow reaction. Okay, that's why the details will be covered in chemical equilibria instead. Okay, let's go on to the second example, catalytic converters. So catalytic converters, they reduce pollution by converting the possible polluting gases, the exhaust gases, on a catalyst and convert it into harmless products. Right? So this is something you have to remember. What are the exhaust gases? You have your oxides of nitrogen, carbon monoxide, and burnt fuels. So they all react together. These are your reactants, and these are your products. So the catalytic converter, the metal itself, is the catalyst surface on which the reactants will pass through, and it lowers the activation energy of these reactants to enable them to react and to convert into these harmless forms. Okay? So essentially, you can also think of it as a redox reaction. So it reduces the nitrogen oxides in the exhaust to create nitrogen gas, and oxygen gas, which is safe to breathe. Reduction reactions as follows. But actually, right, a lot of the oxygen gas which is produced also will then react with the carbon monoxide to form to form CO2. Okay, because carbon monoxide is also toxic, and they also can react with the hydrocarbons to give water and steam. Okay, not water and steam, to give water and carbon dioxide also. Okay, We'll end here for heterogeneous catalysis before we'll move on to the next part, which is to deal with homogeneous catalysis.